Okay, all right.
Well, I was quickly.
Yeah, please.
So we have Dr. Justin Schorr here to give a talk today. He's adjunct professor at George Washington University and also collision reconstruction engineer at DJS Associates. So he's going to be talking about Tesla, Uber, and driverless.
Yes, this. Thank you very much for having me. I apologize for the technical delays and the delays in me arriving just about at 11 o'clock today. So my name is Justin Schorr. I'm an adjunct professor at George Washington University. Actually haven't taught in 1 or 2 semesters because I have a job as a collision reconstruction engineer, which is a private industry job in Philadelphia, Pennsylvania, for a company called DJS Associates, which my grandfather started. My father then took over, and now after getting my PhD, I'm the 3rd generation of Schorrs to be collision reconstruction engineers there. So you might be asking yourself, what exactly is a collision reconstruction engineer? We had that question prior to getting started. And generally, we deal with tort litigation and what happens after you get in a collision. So I think that this video right here, now that we have it working, should be a pretty good introduction to what we do.
Hello. Have you attained your financial goals? Is your economic future secure? Do you have the money you need to buy the things you want?
Do you have the money you need
If your
to
answer
buy
is
the
no,
things
ask
you
yourself
want?
these questions.
If your answer is no,
Have
ask
you been
yourself these
injured or
questions.
shot while committing a
Have you
burglary?
been injured or
Have you
shot
survived
while
a
committing a
suicide attempt
burglary?
made on public
Have you
property?
survived a suicide
Has a
attempt made on
bartender
public
sold you a
property?
drink which led to your
Has a
involvement in a
bartender
fatal
sold you a
hit-and-run
drink which led
accident?
to your involvement in a
If
fatal
so, then we at the
hit-and-run
law firm
accident?
of Green and
If
Fazio can
so,
help
then
you
we at the
achieve
law firm of
financial
Green and
independence
Fazio can
through
help you achieve
litigation.
financial
This sounds too
independence
good to
through
be true.
litigation.
Listen to
This
some
sounds
of
too
our
good to be
clients.
true. Listen to
I
some
didn't
of our
realize it at the
clients.
time, but throwing myself in front of that subway car was my first step on the road to financial independence.
Sure, I'm grateful the medics pulled me from the wreck. But they didn't have to dislocate my shoulder. No one can give me back my shoulder the way it was before it was dislocated. But thanks to Green and Fazio, at least I have my financial independence. The construction site was posted no trespassing.
The construction
But let's
site
be
was
frank.
posted no
What does a no
trespassing.
trespassing sign
But let's
mean
be
when you're as
frank.
drunk as I
What
was?
does a no trespassing
They
sign
can
mean
have
when
their
you're as drunk as
2.6
I
million
was?
back.
They can have their
We'll give you back like
2.6
you.
million back.
Why haven't you sued? Maybe like many
Why
people, you
haven't
think it's
you
too
sued?
expensive.
Maybe
But
like
at
many
Green and
people, you think
Fazio,
it's
we
too
don't see a
expensive.
dime until you
But at
see
Green
3
and
dimes.
Fazio, we don't see a
So why
dime
put
until
your
you
dreams
see
away?
3 dimes.
In
So
life,
why put your dreams
we don't
away?
regret the things we do.
In life,
We
we
regret
don't
the
regret the
things we
things we
don't
do.
do.
We regret
Think
the
about it.
things we don't
You want to
do.
spend the rest of your
Think
life
about it.
wondering,
Do you want to spend the
maybe
rest
I
of your life
should have
wondering,
sued.
maybe I
Dial
should have
1-500
sued?
harass. The extra S is for an extra large.
Harass.
So maybe that's not exactly the type of lawsuit that we deal with all the time, but you do see a number of frivolous lawsuits come across your desk. It's not quite that bad. I will admit that most of the suits that we do see have merit. Now, there are 3 opportunities for failure in our surface transportation system. They're the vehicle, the roadway, and the driver. There's a famous statistic that I will talk about later, and which of these 3 causes the most collisions? The driver. And does anybody know the statistic that is thrown around in almost every media story you hear, or anything on the topic of why we need self-driving cars? Does anybody know the percentage of crashes that are caused by human error? 94%. No, you guys, nobody listens to the news, nobody sees all these articles. 94%, 94%. It's blasted. It is true that if you think about the system, and I'll talk a little bit more about why that's a faulty logic, even offering that number a little bit later. But if you think about the system, the driver is going to be the weakest component of this system. We understand how to geometrically design our roadways. Our vehicles are mechanically generally, nearly perfect in terms of their mechanical operation. But we as humans, we make tons of mistakes. So if we're looking at a crash and trying to determine which of these three aspects failed or if multiple failed, then for each one we have to dive down a little bit deeper and we have to look at the specifics. So in terms of the vehicles, we're normally dealing with the braking performance of the vehicle, the handling, which includes the steering, and then you have the crashworthiness aspects such as occupant protection and body integrity. Now, intrusion into the occupant compartment is the most important thing that we're trying to reduce for safety. But, you know, the typical failures that we see in terms of vehicles will generally come with the mechanical systems, although crashworthiness is obviously that is a big deal as well, in that there's an expectation for how your vehicle will perform in an accident. In terms of the roadway, here we're generally dealing with geometric design and traffic control issues in terms of what people at least attribute to have failed during a collision. Pavement condition, the striping that goes back to the traffic control, as well as the signage. These are generally what we're looking at. It's amazing to me to see that if somebody is involved in a crash and there were 5 chevron signs, well, the argument is that if there were 6 chevron signs, there's a tongue twister, then obviously the collision would have been avoided, correct? You know, if you have 6 instead of 5, that makes it that much easier to see the curve. Nobody truly believes that, correct? You know, if you have 5 chevron signs, it's probably pretty recognizable to the approaching operator. Generally, can we get some nods? You know, I wanted to come up here so we get the live audience much better. Okay, that's a little bit better. Now, our final component, and this is a pretty good example of some of the excellent decisions that humans make in life. The driver is the weakest component in the system, and when we're dealing with surface transportation and collisions that occur on the network, then obviously we're most concerned with whatever that weak link is. Now, we as drivers are apparently the weak link. We have to perceive, we have to identify, we have to evaluate, we have to make decisions, then we have to actually physically act on those decisions, we have to try to avoid collisions, and we have to execute a number of different driving maneuvers based on whatever situation we come upon. Now, when we look at collisions at DJS, we have our analysis process. And being from Philadelphia, we always trust the process. Oh, that's one slide too many. So we always trust the process in Philadelphia, obviously. Now, on the left side there, you see what we'll think of as the macro tasks. You know, we have to collect the data, which generally involves going out to a collision site and then to see the vehicles. We use 3D laser scanners to map the collision site. As well as to take measurements of the vehicles. Now we've actually gotten into using drones to do a lot of the mapping at the sites, and if anybody's worked with drones and the 3D models that can be built up out of the photographs, it really is pretty incredible. Once we get the data back and we collect other data too, such as traffic counts or the police report or any other physical evidence or data that is associated with the collision, then we take that back and analyze that. I'll get into the analysis in a second here. After we're completed our analysis, we render our opinions, and then obviously we want to demonstrate our results, whether it be through a report or in court or at a deposition or however. Now, when we're doing the analysis, because this is really what I want to focus on today, we're looking at you know, I have 6 listed here. These are generally what I could think of on the spot as the six major things that we're looking at during our analysis. So we're taking all the physical evidence, the point of rest of the vehicles, the point of impact, any gouge marks, any tire marks, any scraping along the roadway. We're plotting that you know, with the 3D measurements. We're taking photographs from after the collision, and we're now that we got the sound, it's going to do that the whole time, right? We're taking the photographs of the physical evidence after the collision. We're using photogrammetry and camera matching and other techniques to place that evidence at the collision site if we don't have, if we weren't able to document that. Then the big thing that we're always trying to determine is speed. Now, I'm not saying that every collision we come across we're able to make a speed calculation, but speed is the #1 thing that we want to know, because speed is going to define all the time and distance relationships, and how either two vehicles or one vehicle or multiple vehicles came to arrive at the site of a collision. Once the vehicles are there, we take a look at the dynamics. The conservation of momentum is an analysis technique that if we have sufficient data, that's something that we'll apply. We use things like PC Crash and other simulation programs to look at the dynamics. Then, the occupant movement is not something generally that we're focused on as collision reconstruction engineers. That's more for the biomechanists, but it's certainly important, especially in terms of rollover collisions and trying to determine who was the driver in a rollover collision, how the occupants are going to move when they're exposed to certain collision forces. We go and we look at additional contributing factors to the collision, as well as other considerations, whether it be the design of the roadway, a construction project, or any other of almost an infinite set of contributing factors that you could come up with. We're going for them after, obviously, we've evaluated the collision to the extent the data will allow. Now, the first example I wanna use here is from 1982, and this would have been when my grandfather and my father were doing this analysis together. And what we have here is there's a center line on this roadway, I believe. I don't know if it's painted or not, but it's a two-lane, two-direction roadway, so one lane in each direction. And what we had was we had a vehicle pulling out down here and a motorcycle coming down the roadway. A collision occurs at the intersection. This is, you want to call it almost your classic left turn collision. So left turn cases are one of the most common accident collisions that we see. Here, the physical evidence consisted of tire mark left by the motorcycle as it approached the collision site. Can anybody tell me which of these two tire marks they believe would have been attributable to the motorcycle? Come on, grad students. You guys are all engineers. Which one of these two tire marks looks like it came from a motorcycle? I'll give you a clue. There is a wrong answer and a right answer. So you're saying the one on the right. Why does the one on the right look like it came from a motorcycle? It does. It does look more narrow than the one on the left. And the main thing that we're looking at here is what happens to the direction of the tire mark as you move down. Now, is anybody here a motorcycle operator? Has anybody driven a motorcycle before? Okay, as you try to brake a motorcycle, get a little bit of wobble in the front end, and you get irregular tire marks, as we'll call it. So inevitably, when we go to court, what is somebody going to say if we select the right tire mark as the one that we believe is attributable to the motorcycle? They're going to say, why didn't you use the tire mark on the left? So that, in terms of here, we're talking visual analysis, but if we were going to defend this in court, we would use photogrammetry. We'd actually get the width of those tire marks using the common points in the photograph, and we'd show that tire mark on the right has to be from the motorcycle as opposed to the tire mark on the left based on the tread of the tires. So we go out to the scene, we take some measurements. These measurements were likely done with a wheel and a tape measure and a pen and a pad of paper. That's, I believe, how my grandfather used to do it. Ever since I've been involved in the company, we've had either total station or we've had laser scanners. So other than my training, there's a standard accident reconstruction course. Other than having to go out and plot a scene for that, I don't know that I've done too many of these hand measurements. Go ahead.
What was the tire mark on the left? Because it wasn't a car, it was single.
Right, and that I couldn't tell you what that was from. It could have been left there by a vehicle that had come through days prior or weeks prior. Not all wheels that lock up are going to leave tire marks. So when you're braking, you could have 4 wheels locked, and you could have no markings on the roadway. You could have markings from 3 of the wheels, 2, 1. You're not going to see a general consistency, but a specific consistency between the markings as, you know, if this car was braking, it certainly left marks. So it's never going to be a one-to-one relationship like that. Well, what we do is we go out and we take the measurements, we plot it on our very basic 2D plot that we have here of the collision site, and then we can place the vehicles based on the testimony of the operators, based on the damage to the vehicles. We can determine an approximate angle of impact, place them at a point of impact consistent with, let's say, a gouge mark or other physical evidence left along the roadway, and now we have what looks like a collision. So, you know, the individual is coming down, and I think I probably said it wrong earlier. It looks like the individual is turning left into the street, and the motorcycle is coming down, and for whatever reason, a collision occurs. Now, the first thing that we're going to do is we're going to use that tire mark to try to determine how fast the motorcycle was going as it approached this collision site. So how fast was the motorcycle going here at the onset of braking? Now, we all remember our 4 kinematic equations, correct? They're the kind of important ones, right, guys? I know that we're civil engineers and not mechanical engineers, but we still do need the equations of motion for civil engineering, right? A little bit. Okay. So that 88 feet of tire marks. Generally, we see a coefficient of friction on a dry roadway of 0.7. That is your typical value. You know, it could be obviously a little bit higher. It could be obviously a little bit lower. With a motorcycle, he could have been using his front brake only. He could have been using both brakes. So, you know, if you're only using one brake as opposed to 2 brakes, then obviously the amount of available friction to the motorcycle is going to decrease. So here we have to make the assumption that he's using both brakes, and we're going to calculate the speed at the onset of braking. So here the speed of the motorcycle, consistent with that 88-foot tire mark, is, I believe it was 41 miles an hour. Now, from that 41 miles an hour, we get this green distance right here. Does anybody have any idea what they think that green distance is? What happens before you brake as a driver? What do you have to do first? You have to have a reason to brake, right? There, your reaction. Correct. So this is your perception plus reaction time here. The middle of the bell curve, you'll see a million different studies on this. Generally, the industry accepted value is 1.5 seconds for perception plus reaction. We know that can often be faster. We know that can often be slower. A lot of times it depends on the type of reaction that the individual has to have, whether it's a simple reaction or a complex reaction. But in general, that 1.5 seconds defines, you know, how long it takes the average human, or the typical human, will say, to perceive, react, and then we have the stopping distance. So now that we have this distance, and we know that the motorcycle is traveling 41 miles per hour, can we simply assess fault based on this knowledge? Moms, if I tell you the speed limit on this roadway is 25 miles an hour. Is it certainly the motorcycle's fault that this collision occurred because it was exceeding the speed limit? No, it's not. Because this vehicle that's making the left-hand turn, if the motorcycle is going 41 miles an hour and it's 10 feet from the point of impact and the vehicle decides to make a turn, does it matter how fast the motorcycle is going? Obviously not. Now, if we're going to use that 1.5 seconds, if the motorcycle at the posted speed limit of 25, which is going to be about 37 feet per second, which means that you can perceive and react in, let's see if I can still do math in my head. I think that'd be about 55 feet at 1.5 seconds. If anybody wants to do that in a calculator, you can see how accurate it was. So we have, that would be 55 feet if you're going the speed limit. So if the motorcycle is less than 55 feet from the vehicle when the vehicle decides to make the turn, then no matter what, you cannot say, you know, the motorcycle had sufficient time to perceive, react, and avoid the collision. So what we do is we back up the clock. So we know that at this point, this is when the motorcycle operator, based on this 1.5 second time and the tire mark, this is when where the motorcycle was when he saw that vehicle turn. So what do? We back him up to that point, and then, well, there we go. And then we use the speed limit. So it is 55 feet. So the speed limit was 25 miles an hour. with the same coefficient of friction, you're looking at about 30 feet to stop and 55 feet to perceive and react. So if the motorcycle operator, at the point he perceived the left-turning vehicle, had he been traveling the posted speed limit, he would have been able to perceive, react, and stop in 85 feet, which leaves him 98 feet away from the point of impact had he been traveling the speed limit. Now this sort of analysis is fundamental to what we do in collision reconstruction. So there's rarely an instance where if you have two vehicles involved in a collision, there isn't an avenue by which one or the other vehicle could be assigned a percentage of the fault or the entire fault or generally just be a contributing factor to the collision through some sort of negligence or improper maneuver or whatever you have there. So it's not always the case where just because you're speeding, a collision is your fault. Now, there could be cases where that contributes to a more severe impact speed or something along those lines, but that's where we start to get into crashworthiness and the difference between the damage and the injuries if the collision occurred at a higher speed versus a lower speed. Do we have any water? Sorry. So we saw 1982. Now we're going to move to today. Oh, we did have one more video. You guys are probably too young for this movie, to tell you the truth.
Hey, doctor, better back up. We don't have enough road to get us 88 roads. Where would it go? 88 roads.
These would be a much better idea than self-driving cars, right? Like if everybody could have a drone, that would be very nice. That really fly around. So the first thing I want to do here is define some terminology. This is what I find to be the most misused, the most misused terms in this field, and that's automated vehicles versus autonomous vehicles. Now, coming in here today, is everybody aware that there's a difference between these two? So who here has a car? Does anybody in here? You guys are all in New York City. I forgot. This is going to be zero. 0 people in here have a car. Oh, that's special. All right. So anybody, let's pretend that somebody in here does have a car. So, well, I have a car. Now, my car is a 2015. My car has lane keep assist, and terminology is important here because lane keep assist and lane departure warning are two very, very different systems. My car has lane keep assist. It has the automatic emergency braking. I think it's called brake assistance, and it may have another automated feature or two on it. So those are automated features. I drive an automated vehicle. My vehicle has automated aspects to it. It can take over one of the 3 safety critical functions. In some instances, some of the vehicles now can take over 2 of the 3 at the same time, but the vehicle requires my input to be able to operate. An autonomous vehicle is a closed loop system. The reason that Waymo can take the steering wheel out of their self-driving car is because autonomous vehicles, the essence of them, the foundation, they are closed loop systems. They don't require an internet connection. They don't require a driver. They don't require steering wheel, pedals, no external input. The vehicle is able to do the 3 things that every robot must do. It's able to sense its entire environment. It's able to make a plan based on what it senses, and then it's able to output that plan in terms of control of one of the 3 safety critical functions. Now, what are the 3 safety critical functions in a vehicle? I know that you guys don't drive, but there's only 3 things you really need to do to operate your vehicle. Anybody think of what they are? Was 11 a.m. too early for you guys? Come on. So what is the main thing you do? How do you make the vehicle move? You accelerate. There's 2 of them, accelerate and decelerate. So you accelerate and you brake. Those are 2 of the 3. What's the only other thing you need to do? Park, yeah. Especially in New York. Find a parking spot could be considered a critical function. But I heard it over here. It's turn the wheel. So really, everything else in our vehicle, we only need to do 3 things to make that vehicle move along the transportation network. Now, the autonomous vehicle has control over those 3 functions at all points without any input from a user. An automated vehicle takes over one of those systems, maybe 2 of those systems in unison, but at no point can an automated vehicle operate fully without any input from some externality. Now, the SAE conventions, has everybody seen this before, the levels of automation? And I do think this actually, I feel like this catches a lot of flack in not only in the research community, but in the consuming public as well. The levels of automation aren't perfect, but they're very difficult to define in a way that has any practical implications. So these, while not perfect, I do believe that they serve some purpose in terms of kind of delineating the data for us. But when we think of levels 1 through 5 here, levels 1 and 2 and parts of level 3 can be thought of automated vehicles, and levels 4 and 5 and also parts of 3 again can be thought of as autonomous vehicles. So even though level 4 is some specific use cases, to tell you the truth, I don't see a huge difference between level 4 and level 5 the way that it's presented. If you think of it practically, any disengagement, you'd have to have ample warning for the driver to take over. So level 4 vehicles, I don't know that that's something that's ever going to truly come to fruition in the way it's described. Good.
The US DOT actually changed this whole bit. Now they have 3 keys, like levels: driver, partial automation, and full automation.
Okay.
They kind of realized it's not necessary to have 2 different things or 3 different things before partial.
Perfect.
Full automation.
So they took what I had here and
they're going to require the driver to be in to start with, but then they might remove the driver, but it's still part of full automation.
well, that's actually good to see, because it seems like I have level 0, level 1, and level 2, right there. So we got 3 here. That works for me. I'm not sure if they're exactly the same, but that's good. And I know that that's something that's continuously being developed, because the way that these vehicles are realized in our world is something that we're not sure of yet. We're not sure of the use cases. We're not sure of even how this plays out in terms of getting these vehicles on the roadway. Now, the decision-making framework. I talked about sense, plan, act, which is your fundamental law of robotics. At each one of these levels is really where the failure can occur with an autonomous vehicle. Now, we're an automated vehicle, for that matter, in terms of the specific systems. Now, in terms of liability, this is where we start to get into some difficult or some murky waters. I think that's the term. So at each of these levels, has anybody ever seen what the transportation, they're calling transportation stack, or your self-driving stack, looks like today? All the different companies that are involved. One company makes the sensor, another company makes the processor, another company makes the motion control, and you have, and they're all, put on a third OEM's actual vehicle. So you have a lot of different players on each of these different levels, which means that if a failure occurs, it's very important to determine which part of the system the failure occurred in. Now, the one statistic to rule them all, and this is what I kind of introduced earlier, and that's this number. This didn't turn out too bad. Okay. So this is Traffic Safety Facts, February 2015 from NHTSA. 94% of all collisions are caused by the driver. Is this statistic worth anything?
I don't think that is that important. That number is important.
Exactly. This is what's important. And obviously we need the denominator as well, which is some measure of exposure that we can use. But this number, this 94% of collisions are caused by driver error, it means absolutely nothing. All that this means is that the infrastructure and the vehicles fail, and I guess that your unknown makes up some of it, but approximately 2% of the time for each of them, that's when our infrastructure and our vehicles fail. Now, that has no, again, practical significance. We would want to use the actual counting variable with some measure of exposure and then go through, and obviously this would require some rigorous statistics to actually come up with a metric that demonstrates and this is something that's, I know you said traffic safety was your study area. It was mine as well, and that's generally, we're always trying to develop surrogate measures for safety, correct? We're coming up with a new way to measure safety that is more telling or more revealing than the old way, whether we go down to the micro levels or up to the macro levels. We're always looking for a surrogate measure for safety that's new and improved from the old ones. Now, here we do need a better measure for safety other than just keep repeating 94% of collisions are caused by driver error. Well, if there's 1 million collisions and 500,000 of them are caused by driver error, then only 50% are caused by driver error. But if there's 1,000 collisions and all of them are caused by driver error, 100% are caused by driver error. Which one of those two seems like a safer environment? The one where 1,000 collisions are 100% driver error, or the one where 1 million collisions are 50% driver error? Obviously, the first scenario is going to be what we view as a safer environment. I think more focus needs to be paid to those counting variables rather than the percentages which just get thrown around all the time. But one of the principles that applies to this and throughout a lot of what I do now is Hamlin's razor, and that you can never attribute to malice that which is adequately explained by incompetence. I think that this principle actually applies pretty vastly throughout the autonomous vehicle and self-driving and automated system landscape. And it's evidenced right here. A little loud one. This is Volvo testing the pedestrian detection system. I don't know if anybody's seen this before. So that video is a little bit old. It's Volvo testing their pedestrian detection system, and it looks like it's outside some dealership or research facility. Obviously, it doesn't pick up the pedestrian. The vehicle hits the guy that's standing there. Now, when is that acceptable on our roadways today? I'm not saying that specific failure is something that Volvo didn't go back and look at and fix, but how many of those failures, is that failure something that is acceptable if you're walking down the street? Do you think a human driver could have avoided that collision? Obviously, it's a test, but we just saw that Uber crash in Arizona. What happened to that Uber crash? Well, pedestrians walking a bike across the roadway, the Uber vehicle, for whatever reason, doesn't detect the pedestrian, no stopping or slowing prior to impact.
I think it was more complicated.
And
it's a classic failure. Like the car was fully autonomous, it just hit the guy. But I think in the other case, it was like so rapid that the real driver would have the same problem. But here, the driver would just stop.
And we did, and I've looked at that video, and a real driver would have difficulty avoiding that collision, and it's not something that I've analyzed to the extent that I'm able to present to you something that I would be comfortable defending in court, which is the way that I would always have to think about almost anything I say in this field. And that's that Uber crash there. I'll leave it at, I do believe that there is a possibility a human driver could have slowed the vehicle to a speed to a speed less than the impact speed that occurred. I'm trying to be very careful about how I say this, if you can't tell, or avoided the collision altogether. I do believe that there was an opportunity that if human driver could have perceived and reacted in a short enough time frame to be able to at least mitigate the severity of that collision. So that's where we'll leave that one for now, and hopefully at the end we can discuss that a little bit more. I want to talk about the Tesla crash in Williston, Florida today. So let's start with the systems on the Tesla vehicle. And good, this came up. All right. So we have a narrow forward camera, a radar, forward-looking side cameras, ultrasonic sensors, rear view cameras, side cameras in the rear, wide forward cameras, and a main forward camera. All of these have different applications. So, the ultrasonic sensors aren't going to be very good for determining the distance to a vehicle that's 500 feet away. We'd use something like radar or one of the forward cameras in those instances. Now, if the vehicle's trying to back into a parking spot, that's when we're going to be reliant on those more micro-level systems. Now, how do we classify these systems is something that is of incredible importance to moving forward in the world where we have a mixed environment between autonomous vehicles or semi-autonomous vehicles and completely human-driven vehicles. So are these safety systems? Are these assistance systems? Are they convenience systems? I'm sure we could think of a couple other adjectives to describe them and ask the same question, but really determining what type of system this is very important. What type of system is your airbag? Your airbag would be a safety system, correct? Everybody agree with that the airbag is a safety system? Active safety, passive safety, yes, come on. bring up the mood a little bit. So our airbag is a safety system. If we get in a crash and the threshold's met and the airbag doesn't deploy, is that acceptable? We have a reasonable expectation that an airbag is going to deploy under the scenarios that are laid out for airbag deployment. We consider airbags to be a safety system. When that safety system fails, there's a problem. Now, if an assistance system fails, does that constitute the same amount of problem? Do we have the same expectation of that assistance system that we do of the safety system? Has anybody been in a vehicle that has lane keep assist on it, lane centering? Does it work all the time? No, it doesn't. I mean, it's not that the system's bad, but the system is not going to work under all scenarios. What was that? Oh, so you've been in a Volvo. Let's not show this to anybody from Volvo. That's so when an assistance system fails, there's as drivers we expect that there is going to be some failure in that assistance system. Now, a convenience system, if our AC goes out, well, if you get in a crash because your AC is out, well, I think that's probably a little bit your problem, not a generally contributing factor to the happenings of collisions. So this is, it didn't work, did it? Oh, there we go. I was able to get it. So this is from Tesla's website. They define the side collision warning and the emergency braking as active safety systems. So should there be an expectation that emergency braking system will brake the vehicle if there is a hazard in front of it? There should be an expectation, correct? Now, when that becomes mandated by FMVSS, does the expectation suddenly arise then? Because I believe that's 2022, that the all vehicles must have the forward collision or the brake assist system on them by? Does that sound right? Maybe? Okay. So I do believe it's 2022 that the mandate is for. Once that happens, does it become a safety system, or by defining it here on their website and other literature, is Tesla then saying, okay, this is a safety system? And then is it beholden to the same expectations as other safety systems? So getting into the crash, you're going to see that this is going to play a significant role. May 7th, 2016, Williston, Florida, about 4:40 p.m., sunny day, no adverse weather conditions. What we had was a tractor trailer that was making a left-hand turn down here, and the Tesla vehicle was coming, which would be eastbound down the roadway this direction. This is the area that I looked at for the analysis. Now, this extends actually back a little bit, but in terms of the cropping, it didn't work. But what you see here is the elevation of the roadway in that area, which is from LiDAR data that the USGS actually collects for almost all of the country But you can see basic, I think that's as accurate to about 2 feet, the USGS. But you got the elevation data. It's overlaid onto the orthomosaic of the collision site there. And we can use this sort of diagram for the analysis, since obviously, I wasn't able to go out and survey that intersection down there in Florida prior to our discussion here today. So, the publicly available data is fairly good. It's fairly accurate, and it can be incredibly helpful in terms of analysis. Now, one of the things, and I'm kind of going to jump around in terms of the collision here because we have limited time. How much time do I have left is the question. Okay, perfect. So I explained to you that it's a left-turning tractor-trailer impacted by the eastbound Tesla. So NHTSA, they put out a bunch of data on this collision. You ready? This is the totality of the documents, less one report that NHTSA has for this collision, and they also put one Excel file relating to the ADAS systems, the advanced driver assistance systems in the vehicle. So PC crash is something that NHTSA used and something that we use commonly at the office. We have one guy at our office who's one of the smartest people that I've ever gotten to work with in anything, and he is incredible with PC crash, and he did me a huge solid, and he went through and to the best of the ability at this point. And again, this is still what we would consider to be our preliminary analysis of the collision, but he went through to the best that he could based on the limited time and data availability, and recreated the PC crash that NHTSA did as well. So what you see here is the vehicle, and that's the Tesla vehicle coming down, and we have the tractor trailer making the turn. Now I'm just going to run it down a couple more frames. These are 1 second apart. Now we get the close-ups. This will be easier to see. Okay, so let's work our way backwards from the impact, because generally in crash reconstruction, that's what we do. So at 1 second, we're here. 2 seconds prior to impact, we're here. 3 seconds prior to impact, here. 4 seconds here. 5 seconds there. Okay. When does this tractor trailer become a hazard to the Tesla? So we're always looking for which vehicle or what created the initial hazard that led to the collision. For a left-turning vehicle impacted by a vehicle that generally has the right-of-way on a through street, the hazard that led to the collision is always going to be the left-turning vehicle, because it's turning across a street that has the right-of-way. Now, when does this left-turning vehicle become a hazard? If we backed it up further, is it when you start to see the tractor-trailer turn into median? Is it here as the tractor-trailer starts to cross into the turning lane? Or is it here as the tractor-trailer starts to cross into the actual travel lanes, or I shouldn't say that, the actual travel, or the two through lanes along this roadway? Anybody have an opinion as to when that would constitute a hazard? There's no wrong answer to this one, I'll be fair. When would you start to brake if you were driving? Or when would you at least perk up and realize that maybe you'll have to do something as you approach this intersection? You think it's this frame, maybe further in, that frame? Somebody give me one opinion and I'll move on, I promise. For the Tesla driver. He has to see the car, right? He has to see the car. Right, and I should say there's no sight distance restriction here. So the Tesla driver can see the tractor trailer back to where it was in the left turn lane. Tractor trailer can see all the way down clear and see the Tesla driver. There? Okay, so he knows he's making the left turn. Correct. Now, in terms of analysis, we would take this to be where the hazard is defined, because this is where the vehicle really starts to cross into the travel lanes. However, and I'm glad you said this frame, because anecdotally, I was driving back from a site inspection 2 weeks ago, and the guy who was driving our car, we were in Philadelphia, a pedestrian was walking down the sidewalk and made a turn like they were going to go and cross the street. Now, we had the green light, and they had a don't walk signal, and they did stop on the sidewalk, but the guy who was driving our car slowed our vehicle a little faster than you would normally do in anticipation that there might be a potential conflict there. Can an autonomous vehicle, and this is stepping outside the Tesla crash, is that something that current autonomous vehicles can do? Or would we as humans be better decision makers when it comes to determining if there's a potential path intrusion rather than an actual path intrusion? You look like you want to say something.
I think sometimes humans are better.
And I think that this is one of the cases where, are we going to ever be able to perceive and react as fast as a computer? Unlikely. Now, are we going to be able to predict better than a computer? Almost certainly. Or predict future movements, I should say, better than a computer? Almost certainly. The thing that we as humans are best at is determining utility. So we could see a chair, or we could see an upside down cardboard box or a stump or something else, and we would see something to sit on. A computer is not going to see that when they look at a stump versus a chair. It doesn't see the utility of the object that it's looking at. We as humans see the utility of that object, and that's something that really aids us in our object detection, recognition, and then decision making afterwards. So defining this as and let's go one forward. The analysis doesn't work as well if we define it back there. Let's define this as where the tractor trailer becomes a hazard to the approaching Tesla. We have 1, 2, 3, 4 seconds until impact. How much braking is anybody familiar with this crash? Has anybody looked at this at all, heard a news story, anything? How much braking do you think the Tesla vehicle did as it came down? None. Tesla vehicle in this crash did not brake at all. In determining avoidance, and this is what we're going to do in terms of the reconstruction, the traditional approach says, okay, let's see if we're going 65 miles an hour, which is the speed limit, on a roadway with a 0.7 coefficient of friction, which is typical, and then using that typical perception plus reaction value, the distance to perceive, react, and stop is approximately 345 feet. Now, without stopping or slowing, we would travel that 345 feet in about 3.6 seconds. So that defines 3.6 seconds, how long we need to view a hazard to be able to perceive, react, and avoid that hazard. That is, we'll call it the hazard time or whatever we want to call it. That 3.6 seconds is what we need. So if that tractor trailer is out there for 3.6 seconds, then under typical assumptions for the perception plus reaction time and the coefficient of friction, a human driver should have the ability to perceive, react, and avoid the collision. If we went to court and this wasn't a Tesla, this was just somebody driving a 1992 Toyota Camry, and they did not perceive, react, and stop prior to impacting the tractor trailer, there would be a serious question as to if that operator was paying reasonable attention to the driving task as they approached the area of the collision, and whether or not the tractor trailer did indeed move into the path as a hazard without providing sufficient opportunity to avoid the collision for the approaching operator. So, the traditional reconstruction says that tractor trailer was out there for about 4 seconds, and you only need 3.6 seconds to be able to avoid it. So the traditional reconstruction approach says this collision was either avoidable, or the severity could have been reduced, or potentially even, and you get this with some of the higher distances, potentially even depending on the speed of the tractor trailer at impact, tractor trailer could have moved down further across the roadway and cleared the path of the Tesla prior to the Tesla arriving at this location. The Tesla was traveling 74 miles an hour. So, in terms of this collision specifically, it's not something that really plays, but if we're looking at, and I think I have it here, okay. If we're looking at you know, the avoidance ability, well, if you're going 65 miles an hour, this is your last clear chance to avoid. If you're going 74 miles an hour, this is your last clear chance to avoid. And we all just agreed that 4 seconds was the time that the tractor trailer was visible as a hazard. So either at 74, which was the operating speed at the time of the collision, or at 65, the posted speed limit, the human driver has the ability to perceive, react, and either stop about this much short of the collision or the distance between the yellow and the 65 line. Now, NHTSA defined different scenarios for the acceleration and the movement of the tractor trailer. If we're going to ignore everything else and just look at what we want to get at, or what we're concerned with here, the minimum time that you see that tractor trailer, and this is where we defined it as a hazard. So the front crosses into the eastbound travel lane. So this is where you defined it as the hazard. This is where we ultimately went with as a hazard. So if we go over here, then if that's where the hazard is defined, then no matter what scenario proposed by NHTSA, the collision would have been avoidable. If we go over here, you know, we have three of the 6 are just 0.2 or 0.1 seconds below what you would need to avoid. So if that operator is able to perceive, react in either 1.3 seconds or 1.4 seconds, then they could have avoided the collision potentially. But in general, what we see is that no matter what scenario NHTSA proposed for the movement of the tractor trailer, the approaching operator should have been able to perceive, react, and either slow the vehicle to a speed a lot less than the 74-mile-an-hour impact speed, or avoid the collision completely. Now, the concern here comes with the actual ADAS systems and the data that NHTSA got off of the Tesla after the collision. Has anybody heard of an event data recorder before? What was that? In planes, correct. Now, does anybody know that 90% of vehicles, model year, I think this was in 2010, 90% of new vehicles were being made with event data recorders, and that they're mandated on tractor trailers? No? That's good. So there are these event data recorders that are mandated on tractor trailers that NHTSA provided a lot of guidance for passenger vehicles, and they found that, I think, when they evaluated it in 2010 or 2012, that 90% compliance with having this EDR, and then NHTSA defines which variables you have to record for the vehicle. I hate using text on slides, but this is something that you guys can either go back to later, or we can just look at quickly now. The Tesla Model S was equipped with the following automated vehicle control systems: autopilot, which included the lane change system, the auto steer, the adaptive cruise control, a forward collision avoidance system, forward collision warning, automatic emergency braking, speed assist, lane assist, auto park. These systems were on the vehicle. Later in the report, it says there is no data to suggest that these systems were inactive at the time of the collision. The question becomes, why was no data recorded, stored, or seemingly even picked up by the forward collision avoidance system prior to this collision? So one of the problems with a lot of these systems, and they say this problem in the owner's manual. I wasn't able to obtain the same owner's manual from the model year of the Tesla here, but I know that in some of the Tesla owner's manuals, they say, well, when you have a crossing vehicle, that creates problems for the system. Okay, that's fine. As a crossing vehicle potentially could create problems. Potentially that Uber, their system, which I know was not using Mobileye like this one was, but Uber's system, it hit a pedestrian that was crossing across. Maybe this is simply a problem that these systems have. Okay, let's think about what the system is seeing as it approaches the collision site. Well, if that big box of the tractor trailer is fully across the 2 lanes, is that any different than seeing a wall across the 2 lanes? What the vehicle picks it up as is non-traversable space, as I believe is how they characterize it. So it's space that you cannot drive in the vehicle. So whether or not it's picked up as a vehicle or whether it's picked up as, don't go here, there's a question as to why no data was recorded, stored, or seemingly picked up by the forward collision avoidance system during this collision. This is the data that Tesla, I'll say that, yes, Tesla provided. Because Tesla's data is in a proprietary format. In order for the NTSB investigators to get that data, Tesla has to run the binary through their own filtering system to determine what the binary actually means, and then they turn it over to NTSB. So NTSB says we want this, 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 this. Tesla says, okay, we'll handle it. We'll give you guys the data later. Now, could there be problems associated with a sort of system where the company or the manufacturer is the only person that holds the key to that magic box in determining what that data actually says? Obviously, there could be some problems with this. Now, why don't we solve it with the EDRs? That seems like a reasonable decision. Well, Tesla didn't have an EDR in this vehicle. Why didn't they have an EDR in this vehicle? Because so I shouldn't say why. Let's say one potential reason that they may not have had this EDR in the vehicle, and that's how you couch things, in case you guys are ever in the same field that I am right here. But now I lost my train of thought. You see how that works? That's beautiful. Okay, so where were we? Why didn't it have an EDR in the vehicle? One potential explanation of why the Tesla did not have an EDR is because if they do have an EDR, then that EDR is mandated to record a certain number of variables in a certain format at a certain time resolution. Once you have the EDR in the vehicle, that's when the government regulation kicks in. They define exactly the parameters of how that data is downloaded and what data must be captured and the resolution at which it must be captured. So by not having that EDR in the vehicle, Tesla actually, in the instance of a collision, it provides themselves a little protection in that they are the only ones that can access the proprietary data that comes from all of these vehicle systems, including the onboard diagnostics such as vehicle speed. So the variables here are the variables that were included in the Tesla data set. And all of these variables come into the... Has anybody ever worked with an instrumented vehicle of any type? So this is something that I actually developed or built, quote unquote, as a project for our vehicle instrumentation laboratory at GW. And one of the craziest things about it was that when the data comes into the ECU, each unit that's sending it data, whether it be, especially if it's from a different company, and especially if it's all coming into a laptop afterwards, all of that data is timestamped differently. And syncing that data is a really difficult task. And what we see here is there are aspects of this data set that Tesla provided after the collision that simply, they don't make apparent sense here. So here we have the cruise state and the cruise setting. So the cruise is set to 70 until here, and then apparently it goes up to 73 and then up to 74. This is the detector if the hands are on the wheel. Now, a lot of things that you heard in the media reports about this crash is that the operator didn't have his hands on his wheel for like 90% of the drive prior to this collision. Okay, so what was happening immediately prior to this collision? Well, somehow the cruise is going up, but the hands aren't on the wheel. Okay, it is a joystick on the side that's possible. The engine torque is what we see here. The engine torque is going up, but there are no hands on the wheel. Presumably, and now you guys don't drive cars, so this is tough. If you have the cruise control set and you're just chilling with your hands off the wheel, not that I would ever do anything like that. If you're going to go to accelerate, you're not generally just pressing the pedals without grabbing onto something. I would say that anecdotally and without significant research to back this up. But as I'm driving personally, You know, if my hands were off the wheel, I'm grabbing onto something before I'm doing anything with my feet, essentially. I'm never manipulating the pedals without my hands on the wheel. It would be a very rare occurrence that would ever do anything like that. The engine torque is going up. Whether this is for whether it's because the topography is downhill in this area, and there are some instances in that area where it was downhill, and that's causing the engine torque to go up, it's possible. Or whether it's the cruise control itself. And again, this is adaptive cruise control. What we see here is that it goes from 204 meters, that's the distance from a lead vehicle, and it drops down to all these different values, because up here, some lead vehicle cut in front of this vehicle, not saying it cut them off, but it moved in front of the Tesla, and then it was picked up by the systems as a lead vehicle, and presumably the adaptive cruise control may have adjusted the vehicle speed based on the distance between the Tesla and that lead vehicle. Is that necessarily what happened? Absolutely not. But it would be consistent with the operation of the cruise control. In this collision, the possibility exists that from the last time the driver had his hands on the wheel, and this is another piece of information that I don't know that I have a slide to capture it. Okay, I don't. From the last time the driver had his hands on the wheel until the collision, there were no warnings given to the driver to put his hands back on the wheel. Presumably, the adaptive cruise control may, and I say may also have controlled the speed of the vehicle during that period. So what you could potentially have, and the first part is absolutely that the driver, between the last time he was warned and when the collision occurred, was never giving or last time he had his hands on the wheel and when the collision occurred, was never giving any additional warning to put his hands back on the wheel, and that the vehicle was controlling its own speed to a speed that would have had to have been set by the driver, but above the posted speed limit. Now, I take this with a grain of salt, because if you look at this data further, the cruise setting goes from 70 to 73 here. The vehicle is already going 73 miles an hour, according to this data, prior to that. So something doesn't comport with me that you have this setting changing here, yet the vehicle speed seemed to be changing up here. My guess is that the timestamps are different, and that there may be a little adjustment that should be made there. But then you go back and you look at this lead vehicle distance when it drops. Now, go ahead. Which the lead vehicle? Yes, that's what I was going for. The lead vehicle is going 87 miles an hour, 85 miles an hour. You get an average speed in there. I don't think that the time stamps on the data, I don't think it's 1 second, each time it's one discrete step. To 1 second is like 0.95, 1.23. My guess is that the time stamps aren't completely uniform across, and that's why you see some variation there and in some of the other data. But in general, you have that lead vehicle cut in. That lead vehicle is certainly speeding based on how quickly it's pulling away from this vehicle and our speed, and our vehicle accelerates afterwards. Now, could this be coincidence? Obviously. Could the driver have said, oh, that guy's going faster, I'll increase the cruise control speed? Obviously. The possibility does exist, however, that cruise control was set to a certain value prior, and the adaptive cruise control just simply reevaluated its positioning based on the speed of the lead vehicle. This kind of sums up what the concerns are with this collision. The number of warnings, and I never changed the delta, but the number of warnings between the last time the operator touched the wheel and impact, 0. The time between the last time the operator touched the wheel and impact, 6 minutes, 10 seconds. And the change in the vehicle speed, so the difference in the speed of the vehicle between the last time he touched the wheel and when he got in the collision was almost 30 miles an hour. So without touching the wheel, he either adjusted the cruise control, pressed the pedal, or the vehicle adjusted its own speed over that stretch by almost 30 miles an hour from the last time he had his hands on the wheel into the collision. The one big question, Who is at fault? Now, is the tractor-trailer at fault because the tractor-trailer operator could see the Tesla driver, although if he had been traveling the posted speed limit and a typical human operator should have been able to avoid the collision, is it still the tractor-trailer operator's fault for moving directly into the path of a visible and approaching vehicle? Is it the Tesla operator's fault for not paying reasonable attention to the driving task, although the vehicle was in autopilot? Or was it Tesla's fault for the vehicle not, or seemingly not, detecting or acting based on the tractor-trailer pulling into its path? This is where you have to participate. So who thinks it was the Tesla operator's fault? Let's start. Who thinks it was the tractor-trailer's fault? How about the Tesla operator? So we got 2 for the Tesla operator, and how about the Tesla vehicle? And we got 2 and 3 abstains. And the abstains kind of cheat. So you think it's 50-50 between the operator and the vehicle?
Maybe not, but he should pay more attention. But something that said faulty on the brakes on the data.
Here, this is when the collision occurred, this black line right here. So this is as the vehicle is traveling to its point of rest. Right, so it's faulty likely because a sensor was destroyed or some connection was broken on. I didn't put the damage photographs in here. That's what happens when you don't arrive on time. You don't have time to throw the last 2 pictures in there. But the Tesla vehicle, essentially the top half, it underrode the side of the tractor trailer. The top half of the Tesla vehicle was just torn back, and obviously that got into the driver's body there. Okay. So, but you think that there should be some shared liability here between the 2?
He could cut in at any time. There's no legislation on it, so he could cut in at any time and stop that.
And that's perfect. That's the perfect answer. There's no legislation as to what these systems have to do. Now, as a researcher, it's great, right? I mean, having no legislation means that testing and research are facilitated and made a lot easier. As a user of the transportation system, and a frequent user of the transportation system given my profession, it is very concerning to me the prospects of a mixed environment between human drivers and completely machine-driven vehicles. So fully autonomous vehicles. Now, let's before we move into the broad perspective, let's kind of close this one up. So that mixed environment that I just discussed, and am I over time yet? Okay, so we'll wrap it up quickly here. That mixed environment, there must be some legislation or some expectation that is clearly conveyed to the user about what is acceptable and unacceptable on the part of the user and the part of the car company in those scenarios. Was it okay that Tesla allowed the vehicle to continue to operate without the driver touching the wheel for 6 minutes? Now, they've reduced that time since then, but inviting a driver for any period of time to take their hands off the wheel and their mind off the driving task, that there's a little bit of cognitive dissonance there with NHTSA, because the way we define distraction is manual, visual, and cognitive. And what they're saying is that the vehicle is allowed to distract you in 2 of those 3 ways. So by not legislating or regulating that the driver must have his hands on the wheel at all times while he's driving, then that is allowing the driver to remove their hands from the wheel. Now, if the vehicle is controlling itself, obviously your mind is not going to be 100% focused on the task of driving. We see re-engagement times from automated to self-driving modes. They're widely varying, and I wouldn't trust any, of somebody that says, oh, it's 10 seconds or 1 second or 2 seconds. Yeah, I saw a study that said it was like 3 minutes for somebody to get back. what are you doing for 3 minutes in your vehicle that you can't get back? Okay, so you know, these systems, if we're inviting the driver to be distracted, are we then creating a situation where the lack of regulation and the vehicles themselves are creating a less safe environment for the operators? And should the car companies be allowed to put those vehicles on the road with those technologies without being perfectly clear that it's not an autonomous vehicle, that is not really an autopilot, it's a driver assistance system that's taking over most of the control while you're operating the vehicle under the scenarios that it defines. Now, obviously, you'd have to come up with a little better way of saying that, but in general, I think that the information that's portrayed from the car companies and from the government to the consumer needs to be clear, concise, and much more delineated and regulated than it is right now. Now, just to touch on this, and I promise this is the last thing, and I'll let everybody go. The broad perspective on why. Will we eventually have to make this decision? Can we exist in a world where we have a mixture of both autonomous vehicles and human-driven vehicles? At some point, the answer is no. Like, you cannot get to a point. The suggestion is CASE, right? Connected, autonomous, shared, electric. That's the new and improved acronym that's being used. And essentially, if you have shared vehicles, you can reduce the fleet by 80%, correct? Everybody's heard that research, maybe? Well, that's wonderful. Until we have Hurricane Harvey hit Houston, and we have 20% of the vehicles for 100% of the people, or you don't pay your taxes, and who's controlling this shared pool of vehicles? Well, potentially there's only one entity that's large enough to control what would be a universal pool of vehicles, and that would be the government. Well, maybe you don't pay your taxes, and maybe now you can't move around your world. Autonomous vehicles, and not automated vehicles, but autonomous vehicles, they represent a fundamental shift in how we interact with our environment. I think that there's use cases for them. I don't think that those use cases are on roadways with human drivers. I don't think that allowing a driver to operate a vehicle, even in an autonomous mode, where the vehicle is in complete control of the vehicle is in complete control of itself for a period of time, I do not think that that is fair, let's say, to the human driver should there be a collision. In terms of evaluating that collision, at some point you'd have to develop a surrogate, average human and start debating over what decisions that human would have made under the various different scenarios of the collisions. And the fact remains that right now, what's safer, a human-driven vehicle or the autonomous vehicles as they exist today? Which do you trust more right now? As researchers in this field, you answer this question, presentation can be over. How about that? I know it's a tough one, but you can say it. Humans are safer right now than our autonomous vehicles. The amount of miles that those autonomous vehicles would need to drive on the roadways to get the exposure, to even eliminate the spike in the accident rate from one collision or one fatality is not something that's achievable within the current framework that we have for testing, within the current landscape of people and different stakeholders involved in this community. This sort of evaluation as to whether or not we have this mixed environment is coming, and it's coming very soon. And it's very clear that the push to 94% of collisions, remember, are caused by driver error. So clearly, with self-driving cars, it will be a much safer world. Now, I think that hopefully I've demonstrated to you today that that may not be the case right now. Moving forward, I don't know when the technology will catch up to where it needs to be a valid replacement for a human under all scenarios. When that becomes safer than a human driver, that again, I think that's assumed to be now. I don't necessarily agree that is the case. It's an interesting world, being in liability. It's not the same type of down and dirty research and you know, all the broad, big, grand ideas that I had while I was in academics. There's a hardened practicality to how these systems are eventually realized in the real world. And I think that there needs to be a lot more discussion of that practical implication or those practical implications prior to just unleashing these vehicles as they've been unleashed now in terms of the current testing environment. Yep, 5 years, right? That's when we're going to have full self-driving cars. Everybody's going to have one. Is that how it works? Okay. All right. Thank you guys very much. I really appreciate you coming and listening to me today. Hopefully I didn't bore you too much. So thank you. Any questions?
I have like a comment. Even though we're not going to have maybe autonomous systems, in which we have, drivers and self-driving cars. Of course, we need policies to implement to make roads safer, but there are no algorithms that value someone's life. I mean, self-driving car will try to save your life, but it doesn't mean that it will kill someone else's life, take someone else's life. So, for example, if you have like a group of people waiting, like you kill them, right?
Right.
But
here's
the policy against this. Like, what if I stand in front of a self-driving car, and like what happens to me? It's not gonna hit me for sure.
Well, if it's that Volvo that we watched, it may. or if you're not standing there, if you move from the side, then apparently all the systems they immediately fail, right? That's how it works.
Or like I kind of like just to have fun. I kind of like I get a lot of people who are like standing in front of a car cannot go anywhere, right? But these systems, that's why most of them should be like only self-driving car lane, or it should be divided. So in the future, what you're talking about, you should have maybe separate like self-driving car lanes and then driver lanes.
And well, yeah, keep going. Sorry.
Just what I think is not only going to change the car, this system is also going to change infrastructure. So the way you think it is a little bit different in the future. Maybe in 5 years, maybe not in 5, but it will be an implementation of a new infrastructure just for self-driving cars. Then you can use it.
Right, and you can take that even further. It's going to change the land use. How we build up our communities and our cities. That's why I say it's a fundamental change in how we interact with our world.
Yeah, but the self-driving car in 5 years, the plan is to have a car that can drive itself, not the system, though. The system will take years. I mean, maybe 20 years, 30 years to implement. It's like when they, come up with a car, no one actually built roads immediately. We didn't have like asphalt roads, but it took a while to build that too. So what I'm saying is we might have a self-driving car in 5 years, but then we have to wait for the infrastructure to make it happen.
And I think so the infrastructure is something that I was focused on almost exclusively at the beginning of this and saying, so I've heard from colleagues that are in this research that any sign that's any road sign that's over 2 years old, I believe it is, will have to be replaced in order to be able to be detected by most of the systems that are on the cars today. That's so incredibly expensive. It is just, it's cost prohibitive. Building new infrastructure is not only cost prohibitive, but we're not looking at the same footprint we were looking at when we went from horses to cars, right? The footprint of the United States has changed a lot since then. And let's take New York City, for instance. This is the perfect example. How do you change the infrastructure in this city?
Well, it doesn't have to be physical. It can be cyber-physical infrastructure. So you create like the 3D layer of the city with all the like maybe taking images, whatever you can find. You put them so the way we see maps right now is 2D.
Right.
Maybe in 5 years we can have 3D maps, which you don't need to see anything at all about the infrastructure, so you know where to go. But for all the others, I mean, human interaction is different than all these autonomous systems. Because in an autonomous system, you should not have a human interaction, right?
Right.
It should be like,
Well, there can't be there can't be a human interaction, right? It's prohibited.
you're trying to remove that element, from the system so that everything will be autonomous and, will increase the efficiency. But maybe the way you think what infrastructure is will be, maybe you don't need signs, maybe. You just need an RFID, and that'll be all.
Right. You wouldn't need signs.
Putting an actual physical sign there.
Right. Only in the mixed environment would you physically need the signs, correct?
Those are all for human, drivers. So we can actually remove most of them, like parking lots, we can remove them. Signs, traffic signals.
And this is where we start to get into the discussion of, okay, in this world, do you own your self-driving car? That's the first thing that I always ask.
You need a car. You need to own a car.
Well, so you're saying that the system would be a shared vehicle system. Okay. So now we're getting into that problem that I discussed earlier in terms of if there's a catastrophic event, how do we deal with the demand there? And truthfully, I think that the thing that's overlooked and the biggest concern is if somebody goes to prison, what right is taken away from them? What's the main thing that we're, if you think about it existentially a little bit, what are we doing to somebody that we're sending to prison? We're restricting their ability to move around the environment, right? We're restricting them to a certain place. We're saying you can't move. You cannot physically go around and interact with your environment. Well, in the case that we're talking about, where we share a pool of vehicles, you could hold somebody captive essentially. If who's ever the executor or running this pool, this system, if they don't want to send you a vehicle, then you don't get a vehicle. Now, if all of these vehicles are driving around, and like you said, we need to be constantly mapping, right? Not only constantly mapping, but constantly sharing and mapping. Because the other vehicles obviously need to know what you just detected down here. So if we're constantly mapping the environment, then seemingly we're mapping where Justin just walked out of his house, if there's a vehicle there. So now you're not sending me a car, and you know that I've left my establishment. So the implications, and I know that when you initially think about it, that's conspiracy. The implications that could possibly occur under this scenario are terrifying. I mean, when you start to get into connectivity, you start to get into the problems with hacking and security, and obviously I think that's what you guys said you were working on a little bit, right? Yeah, a little bit. There we go. You're right. Well, think about the problem with tracking somebody. Now, you can make anonymous whatever data you're sending. But if you know somebody when they left, and now you know speed and direction, you know where they went, right? You have all the time and distance relationships from the other data. So no matter how hard you tried to make that data anonymous, data just can't be anonymous based on its own nature. So that the infrastructure would undoubtedly, I don't think the infrastructure physically has to change. I think how we use it has to change. So I think that one of the use cases for autonomous vehicles would be maybe not a city like New York on this scale, but a smaller city. I think that you could shut down a city to personal vehicle usage and only allow self-driving cars to operate within those confines, or at least within some specific geofenced area within that city. And I think that that's how you'll start to see it. Is you'll start to see those geofenced areas where the only option is to prohibit human-driven cars in those areas. At least the way that I see the landscape, that's the only option. So I think that's kind of how that sort of system. I think that will happen. I think that it's something that we're going to see. And it's interesting because you start with a discussion and we could go to 80 different places talking about this. We could take this down a million different avenues. Another thing I think you'll start to see is reallocation of land use within the cities based on how we're getting the vehicles there. So I think you start to see food districts be just food districts and activity districts be just activities. So that if you need to get goods and products in and out of cities and you need to get people around cities, well, it's a heck of a lot easier if all the uses for something are in one area of the city and then all the uses for something else are in another area of the city. So the impacts and how this will evolve, your guess is as good as mine, right? You know, this is just a lot of sitting in the car, driving, and thinking about it, right? There we go. Any more comments, questions? I love having these discussions. They're the best. Like, what do you do in this scenario? They asked people what they would do in this scenario. They said, okay, you have an autonomous vehicle. How should it be ethically programmed? I think there's a little bit of a logical fallacies with some of these arguments, but let's take this one because it makes sense, because it has actual data. When people are asked, what should somebody else's car do if it's one driver versus five pedestrians, what do you think they said? Risk harm to the driver rather than the 5 pedestrians. They're utilitarians in that scenario. But when they were in the vehicle and they were the driver and asked the same question, what do you think people said? Obviously run over the pedestrians, right? Because you don't want to get hurt. That's not okay. You didn't do anything wrong. It's those pedestrians. They walked out in front of your car. And there's so many different interesting little nuances to this whole discussion and this whole landscape. I think that it's important to keep a healthy level of skepticism and in your heads as we all look at this, because you know, it could be somebody who's 15 and somebody who's 50, and it's all about how much you've sat down and thought about this in your experience, and everybody's going to have a different opinion based on, surprisingly, what's important to them. You know, you guys are in New York City. I'm sure you guys would love if there were only self-driving cars in this city and you could actually get places. Like, if it wouldn't have taken me 45 minutes to get those 3 miles, that I could have literally ran faster. Than, maybe not in this current state, but, you know, a couple years ago, I could have ran faster than that. But, you know, that's unacceptable. You look at LA during rush hour. Who the heck wants to be there? Self-driving cars, you know, they get enough of them out there, they will indeed improve traffic flow. Are the benefits, is the juice worth the squeeze? I believe that's the line from a movie. You guys are too young, you know. Any other questions? Let's see. Anything you guys want to talk about? I got to go back home if not. These are some of the ones I like to show. So what happens here? If the vehicle is reliant on the lane striping and the lane striping starts to come off the roadway, all the self-driving cars are just going to stop. And they're going to start. Maybe this, wait, where is it? This is my favorite roadway right here. I don't think this is in America, but whoever designed this roadway, that might be one of the few times we actually see a roadway contribute to a collision. All right, well, thank you guys.